Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Today we will talk about the intermediate value theorem. Let's begin with this activity. We need to complete the table below using the given curves. This is curve 1. Now the question is f continuous or not? Is f strictly monotonic or not? Does f of x change signs or not? And does f of x equals 0 have a unique root or not? Well, you see here f of x changes signs because it goes from negative to positive, then to negative. And f of x equals 0, in fact, in this specific example, has two roots. Let's complete the table using the second curve. F is continuous, f is strictly increasing, so it's strictly monotonic. It does change signs, it changes signs from negative to positive. And f of x equals 0 has a unique root, which is somewhere here. The third curve, C3, f is continuous, f is strictly increasing. F of x, in fact, here doesn't change signs, it's always positive because it's above the x-axis. And f of x equals 0 has no roots. The fourth curve, f is continuous, f is strictly decreasing. You see, f of x changes signs, it's positive, then it becomes negative, and f of x equals 0 has a unique root. And the fifth curve, which is C5, f is discontinuous somewhere here. It's decreasing, then decreasing on its domain of definition. It does change signs, it's positive, then it's negative, also on its domain of definition. Whereas f of x equals 0 doesn't have a unique root. Now this is the table that we completed before. Let's see the question. In your opinion, what conditions should exist so that the equation f of x equals 0 has a unique root? Well, to have a unique root, as you see here, f should be continuous and strictly monotonic, and f of x should change signs. Let's see the property. F is a given function which is defined on an interval I. This is f. If f is continuous on I, f is strictly monotonic on I, and f of x changes signs on I. So if f is continuous, strictly monotonic, and changes signs, then we can say that the equation f of x equals 0 has a unique root, alpha. Now this specific point would be alpha. Let's see property 2. F is a given function defined on an interval I. If now the equation of x equals 0 has a unique root alpha, we do know that it has a unique root alpha, and f of a times f of b is negative. In other words, one of these two values is negative and the other one is positive. They have two opposite signs. Like, for example, if this is f of a, which is negative, this would be a, and if this value is f of b, this would be b. You see, alpha falls between a and b. Remember, if alpha is a root of the equation f of x equals 0, this means that f of alpha is 0, and vice versa. So till now we've seen properties 1 and 2. Remember property 1, if f is continuous on an interval, if it's strictly monotonic on that interval, and if f of x changes signs, then we can say that the equation f of x equals 0 has a unique root alpha. And the second property, if the equation f of x equals 0 has a unique root alpha, and f of a times f of b is less than 0, so we can state that alpha falls between a and b. Let's see an example. We have a table of variations of a function f, and we know that f of 1.5 is 2. The first part asks to verify that negative 3 is a root of the equation f of x equals 0. Now this is f of x, and negative 3 plays the role of x, So we can see from the table if x is negative 3, f of x is 0. So this will be verified automatically, directly. We can just state that f of negative 3 is 0. So negative 3 is a root of this equation. Now the second part asks to show that the equation f of x equals 0 has specifically on the open interval 1 plus infinity, somewhere here, a unique root alpha, and that alpha is between 1.5 and 2. Now here, because the function is not strictly monotonic, we take some restrictions. I mean, we study it first on the interval 1, 2. So between 1 and 2, we can see that f is continuous here, f is strictly decreasing, and f of x changes signs, and in fact it changes signs from plus infinity to negative 4. So from these three conditions applying property 1, we can state that the equation of x equals 0 has a unique root alpha. Now this is the first part of the question, and then we need to verify that alpha falls between 1.5 and 2. This is the second property. We continue, but f of 1.5 is 2, and this is given here, somewhere here, which is positive. And f of 2 is negative 4, and we can tell the answer from the table of variations. So one of them is positive, the other one is negative. So we can see that their product is negative, or alpha is between 1.5 and 2. Now don't forget to study it on the second restriction, I mean on 2 plus infinity. We can see that on 2 plus infinity, f of x equals 0 has no roots. You see here, it has no roots. F of x can never be 0 because its maximum is about negative 2. Note that if you want to prove that the equation of x equals 0 has one or more roots, you need to cover all the intervals over which the function is strictly monotonic. Now let's see this application. This table is the table of variations of a function f, and we know that f of 2 is 1. The question is to show that the equation f of x equals 0 has a unique root alpha, and to verify that alpha is between 1 and 2. Try to solve it alone. Let's see the answer. Well, on the interval negative infinity 1 means somewhere here, we can see that the equation of x equals 0 doesn't have any roots since its maximum is less than 0. This is its maximum, and remember here that 0 is not attained. On the interval 1 plus infinity means somewhere here, we can see that f is continuous, f is strictly increasing, and f of x changes signs from negative 2 to plus infinity. So we can say that the equation f of x equals 0 has a unique root alpha. But we know that f of 1 is negative 2, which is negative, and f of 2 is 1, which is positive. So their product is negative, and we can say that alpha falls between 1 and 2. Finally, the equation f of x equals 0 has a unique root alpha. Another application, this is a curve that represents a function f. The first part asks about the number of roots of the equation f of x equals 0, and we need to justify the answer. Try to do it alone. Now here, remember, when we have the graph, we don't have to go on talking about the intermediate value theorem because you can just see it graphically. So the equation f of x equals 0 has two roots, since c cuts the abscissa axis in 2 points. In fact, these are the roots. This is one of them, this is the other one. Can you find the values of these roots to justify your answer? So f of 1 is 0, thus 1 is the first root, and f of negative 2 is 0, thus negative 2 is the second root. So notice here that if the function is defined graphically, we don't usually use the intermediate value theorem because things would be very clear from the graph. Thank you.